Okay, this is the curve sketching example problems. This is the second video. In this video, we're going to sketch this curve. And so at first glance, it might not look like it with the fractional coefficients, but this is a polynomial, right? So just a coefficient, constant coefficient, x to the fifth, minus a constant coefficient, x to the third, plus 16x. So this is a fifth order polynomial. Polynomials are relatively easy to deal with. The derivatives are easy, no vertical asymptotes, things like that. And then also the domain of a polynomial is all real numbers, as is the range. And then a polynomial is continuous everywhere. It's differentiable everywhere. Okay, so next let's get the intercepts. What are the y-intercepts? Set x equal to 0. Solve for y. So the point 0, 0 is an x-intercept or a y-intercept. Well, it's both actually. All right, now the x-intercepts, set y equal to 0 and solve for x. So we've got, okay, now to get rid of the fractions, let's multiply this entire equation by 15. So we've got 3x to the fifth minus 40x cubed plus 240x is equal to 0. Okay, now let's factor out an x. Okay, so x is equal to 0, which we already knew from here. And then here, to solve this, let's just use our calculator. We already know how to solve polynomial equations and take derivatives and find limits and whatnot. We learned all that in algebra. So to speed up this process, let's use our graphing calculator. This is not an algebra video. Okay, so solve this is equal to 0 for x. Okay, there's no solutions. So there's no solutions to this is equal to 0. So this is the only x-intercept. Okay, next let's check for symmetry. All right, let's check to see if this is an even function, which means it's symmetric about the y-axis. So we replace x with minus x and see if that equals to y, the original function. Okay, this would be plus. Okay, this is not equal to y of x. All right. Now let's check for an odd function. So what is y of minus x? That's okay, yeah, this is equal to y of minus x. See? So this is an odd function, which means it's going to be symmetric about the origin. Okay, cool. Okay, now next let's find the critical points, both with respect to the first and the second derivative. So it'll be faster to use our calculator here. Okay, so now let's take the derivative with respect to x of e. So there's nowhere where this doesn't exist. So let's just solve this for set this equal to 0 and solve. When does the first derivative equal 0? So x is equal to -2 or 2. So the critical points are x is equal to -2 and x is equal to 2. And what we could do is, let's get the actual points. So we've got the original function. Let's do e is the original function with x is equal to 2. All right, so 17.1. So 2, 17.1. All right. Now let's do, okay, minus 17.1. -2. Well, actually, I knew that already because, well, actually, we could have figured this out already because we have 2, 17.1. It's an odd function. So you just, every point you multiply by -1, you get on the original curve. Yeah, so we didn't even need to evaluate this. Okay, now let's get the second critical points. All right, so take the second derivative. Now solve for, so there's no points where this doesn't exist, so just solve for when the second derivative is equal to 0, so -2, 0, 2. Okay, so we've got the second critical points. 2 of them are at the same position as the first critical points. We've also got one at 0, 0, a second critical point. Okay. Now let's analyze the endpoint behavior. So what we do here is we take the limit as x approaches each of the domain endpoints. So in this case, the endpoints are infinity. So what is the limit as x approaches infinity of y? All right, so infinity to the 5th times 1/5, that's infinity. Well, okay. We could evaluate this limit, but to me, it's going to take too long once they get more complicated. Let's just use our calculator. We already know how to take limits. This isn't a video on taking limits. So the limit as x approaches infinity of e is equal to infinity. Okay, now the limit as x approaches minus infinity is minus infinity. So that's the endpoint behavior. Okay, now if we didn't know the function, what it looked like, what we would do then is, for each of these critical points, we would take the limit as x approaches 2 from the left and right, -2 from the left and right. And if that limit, any one of those limits goes to infinity, we have a vertical asymptote. Because a vertical asymptote is only going to be at a critical point, or a second critical point. Because at a vertical asymptote, the function doesn't exist, so that means the derivative doesn't exist. That's a critical point. But the way they teach this in the calculus textbook, the way they teach curve sketching, they don't really do it like this. You just look at your function, and it's a polynomial. We know there's no vertical asymptotes. It's only going to be situations where we're dividing by 0 or one of the trig functions where we'll deal with a vertical asymptote. So we know there's no vertical asymptotes, and we know there's no horizontal asymptotes because we took horizontal asymptotes associated with x going to infinity or negative infinity. And then also, we're not going to be dealing with any slant asymptotes. That's going to be, we'll deal with a slant asymptote with certain types of rational functions. Okay, so what we're going to do next then is find the intervals of the increasing, decreasing intervals and the intervals of concavity. So let's start with we need the first critical points, the critical points associated with the first derivative. Those were 2 and minus 2. So all right. So we know that the first derivative can't change signs unless it crosses over a critical point. So we just need to plug in any value in this region into the first derivative, and then same thing with this region, same thing with this region, to see if that region is, the first derivative is positive or negative. So where is the first derivative? Here's the first derivative. So evaluate this with x is equal to minus 3. Positive. So this region, it's increasing. Okay. Now let's put x is equal to 0. Oh, wait, no, x is equal to 0. That's not a critical point. Sorry. Okay, x is equal to 2. Or wait, hold on. No. Okay, yeah, x is equal to 0. So this is, yeah, x is equal to 0 is not a critical point, but okay. But this is not, it doesn't switch signs over the critical point. So this is not going to be a local max or min. All right, now not x is equal to 2. We want to do x is equal to 3. Okay, so that's interesting. This doesn't, it's increase, we have 2 critical points, but the function doesn't, the derivative doesn't change signs crossing over these critical points. Okay, so now the intervals of concavity, we've got 3 critical points with respect to the second derivative, 2, minus 2, and 0. So okay, so now let's get the second derivative. So there's the second derivative, x with x. Okay. Okay, so minus 3. All right, so it's concave down here. Concave up here. Concave down here. And concave up here. And so this function is continuous everywhere, so these are all inflection points. Minus 2, 0, and 2 are inflection points. The concavity changes signs at these points of continuity. All right, so that's everything. Now let's sketch the curve. And the scale that we're going to use is, so 5 to minus 5 and 30 to minus 30. Okay, first step, let's plot the critical points and the intercepts. So we only have one intercept at the origin. And we've got 2 and 17.1 minus 2 minus 17.1. All right, so each tick, x tick is 1/2. So 2, and then each vertical tick is 3 units. 3, 6, 9, 12, 15, 18. Okay. Okay, so now let's flip about the origin. So 1, no, it would be 1, so 2, and then 3, 6, 9, 12, 15, 18. Okay, now these are the only key points, these 3 points. All right, what do we know about these points? Well, this is just an intercept. So we don't know anything about the shape of the graph here. We could if we took the derivative at that point. But here, these are inflection points and they're critical points where the first derivative is equal to 0. So the first derivative is equal to 0, so we know that we'll have some horizontal lines here, at least right around the point. Okay, now let's draw in between these 2 points. All right, from -2 to 2, it's going to be increasing. Well, it's increasing everywhere, so it's going to be a positive function. It's going to be an increasing function everywhere, so it's never going to be going downward. All right, now from here, from -2 to 0, it's concave up. From 0 to 2, it's concave down. All right, so concave up, inflection point, concave down, inflection point. You see, like this is, I'm drawing an upside down U. I'm drawing a upside down U here. When I'm drawing this, I'm never following a path of a upright U at all. I'm always going in some direction like this. And same idea here. You see, and it's positive, right? It's always positive. It's always an increasing function, and we pass through the origin. Okay. What else? Now, we're going to be positive here, so we're going to be doing something like that. And so I would expect this to be concave up, and it is. All right. And then what is the end point? As x goes to infinity, this function goes to infinity. Okay. I would expect this to be concave down, and it is. And it kind of looks it doesn't look like it's smooth with the way those lines are drawn. There you go. That's it.